continue now.
Thank you.
Our next presentation is about modeling buildings thermal dynamics by Lina. Please welcome.
Everyone, my name is Lina, and I'm a PhD candidate at Kaunas University of Technology. Today I'm going to speak a little bit about different approaches for modeling buildings thermal dynamics and what is the role of these models while developing buildings digital twins. So I guess just to make a small introduction, it's not a question anymore why we should model buildings thermal dynamics. It is a complex process. It includes many parameters, and of course, it's been researched for basically decades now. But if you look into the data, recent data from International Energy Agency, we can see that still almost half of energy demand in buildings was used for space and water heating in 2022. And if we speak about more cold climate countries, this number can reach up to 70% of the whole building energy consumption. So of course, this leads to quite significant CO2 emissions. And what is at the same time important to know that more than 60% of fossil fuels-based technologies were used to cover this heating demand, while the decrease is seen only by 4% since 2010. So if we look into the graph here, we can see that still the main source for the heating energy production is natural gas and oil. Of course, we can see quite high renewable energy penetration. It's not similar in all regions of the world, but we would expect it to double leading to 2030. Another thing what I want to speak about when speaking about building thermal dynamics, that we should look into a more holistic point of view and see how it relates to other emerging technologies in our field, such as digital twins. So we know that digital twins' value lies in the physical realism that can be installed into them. And in this regard, modeling plays an important role. But from the other side, digital twins can also be very useful for the modeling in terms of calibration and validation as well. So again, when we're thinking about modeling buildings thermal dynamics, mostly we would use in two life cycle stages of the building, so design and operation. Of course, it's a little bit more complicated with the design part because we don't have real data yet. But if we speak about the operational part of the building, we can collect data here. And in this figure, we see the green arrows represents the real-time data, and the gray ones is the historical data. So at the same time, for modeling the physical realism, we can use historical data to create hypothetical scenarios for risk assessment, what-if analysis, uncertainty quantification, and process optimization. So all of this can be installed into the digital twins for optimal control, but at the same time for decision-making and public engagement. Another thing to speak about when we are speaking about the modeling thermal dynamics, where it comes to play for the capability levels of the digital twins. So here we have 6 capability levels from standalone to autonomous. And if we look into level 3, this is where the models comes into play. So this allows us to reach the level 3 capability level for digital twins and look at the predictive digital twins, then move forward to the prescriptive that allows us to have some recommendations, and finally reach the autonomous digital twins that can replace the user by closing the control loop. So there are main 3 approaches when we are modeling physics thermal dynamics. So it could be physics-based that relies on resolved, modeled, and observed physics. But of course, the drawback here is that we cannot capture the full physics here. On the other hand, we have the data-driven models that the main benefit is that we can actually capture the full physics, but we lack the insights. And finally, we can have, let's say, the best of the both worlds. And we can use the resolved physics, like physics-based equations that are tuned by the data. So how do we choose this right model? Well, of course, there is no one right answer for that, but we can try to compare different modeling techniques based on the most commonly used criteria, such as model accuracy, interpretability, self-adaptive, evolving models. Transferability is very important, as well the effort and the know-how that is needed to develop this type of models. What is important to note here as well is that even if we speak for, let's say, one criteria, model accuracy, and we look at the physics-based models, and in the research we can find that it is reported that the accuracy for these models can be from low to high. So obviously it depends also on the level of detail and the available data. On the other side, when we have the data-driven models, it is still very dependent on the quantity and quality of the data, but also the model can be very different, right? It can be a simple regression or a neural network. When we speak about the hybrid models, it has basically the benefit that one part can, let's say, substitute or strengthen the another, but at the same time, it has also to suffer from the necessities to complete one or the other modeling technique. So I'm not going to speak about all of these criteria, but I'm going to look at them also a little bit more in the case studies in the future slides. Another way to look into models is also through the asset complexity. So if we try to generalize, physics-based models would work the best when we have low complexity and probably the design stage. So in this case, we can reach a reasonable accuracy, and at the same time, if the building is, let's say, similar to the others or maybe the same, we can even reuse it. When we speak about higher complexities, here we would choose probably more data-driven or hybrid models, especially if we are working in the operational stage of the building and we need to capture the dynamics. And also what it was mentioned already in our keynote speech yesterday and by other presenters, when we have very high complexity, we don't really model in it because we have to balance the trade-off between the efforts and the cost that we invest in our models in relation to the benefits that we get from them. So now let's look a little bit into some case study insights from different techniques. This is a model that is imported in one of the physics-based modeling software. This is a case study actually from Linköping University campus in Sweden, and it is quite a highly complex building. It is combined from 9 floors. It's an academic purpose building that involves huge library spaces, co-working spaces for student group rooms, classrooms, and other spaces. So I don't know if anyone, probably definitely some of you tried to model thermal dynamics using physics-based models. So you probably have seen similar interfaces. You can see how many parameters we actually need to input. And in this case, it's actually quite a detailed model because each room is modeled as a separate zone. We have different set points, and also equipment is also modeled in this model. So you can try and guess what is the difference when we compare the modeled energy consumption to the real data that is existing now. And I can tell you that in terms of this case study, it's by half. So actually, it is 2 times higher than it was modeled here. And this is due to this uncertainty that we have here, where first of all, we don't know all of the equipment that will be installed, will be necessary. Here it was very funny because they have these rooms with hundreds of microwaves for the students, and they just go and heat up their meals. And basically, that's why the electric consumption just goes very high. And of course, when we don't model all of the consumption, it influences the heat balance of the building. And just to put it into perspective, looking into other case studies in the research, it even reported that it can differ from half to 2.75 times. Now looking into the data-driven modeling, I'm not going to speak about the comparison of the performance parameter between different data-driven models, but my point here is what I want to say, that still here we need to make some kind of approximations when we are modeling in this type of way. So for example, here is the same floor plans from the building in Sweden. And it's a very common thing that, for example, when we model building thermodynamics, especially for buildings that are heating with a district heating, we have the energy consumption for the whole building. But then, for example, in this case, it's implemented a rule-based controller based on the CO2 and indoor temperature. So we have data for separate rooms in the building. But we have the energy consumption for the whole building. So we need to make some kind of approximations and cluster the rooms if we want to make some kind of useful models for the control applications. So here it was a very simple approach taken using PCA to cluster the rooms. And we came up with these 3 main clusters. And that it also brought its own challenge, because as I mentioned, it's a very controlled environment. So in cluster 1, we can see the energy consumption is more or less compared to the cluster 2 or 3 covering the space. But in cluster 2 and 3, we see that in the top left and the bottom right corners, we don't have any data points. So again, now we need to make some kind of approximations, maybe create synthetic data by physics-based models. We could use, let's say, weighted least squares to give more weights for the real data. But in the end, we still need to make some kind of assumptions while developing the data-driven models. And finally, I want to share some insights for the another case study that is back in Lithuania for the residential buildings. So here it is already an integrated digital twin that has a real-time data stream and also the 3D representation of the buildings. And we also have integrated hybrid models in this digital twin, which was from a very interesting study that was done in the Netherlands that analyzed 250 buildings. And what these models promise is the reusability, which is very exciting because this is what we want, right? So these models are based on stochastic differential equations, and they're written based on RC. So we are predicting here resistances, capacitances, useful window area, and heat transfer coefficient. And what was very interesting that the models performed, so for example, we are extracting some time period from the data set, and we are fitting the model, and based on the proposed statistical parameters, they worked really well. So it was very interesting to see. But what we have noticed while making a lot of experiments in this type of modeling, that even for the same building, if we take, let's say, a week of data from one month or the other, we can have very different results for example, capacitances or resistances, which in general should be a stable parameter, right? So in this case, we can say when we are optimizing using the statistical parameters, we are losing the most important part of hybrid models, which is the physics, right? In this case, having the digital twin and bringing the human in the loop back could bring some kind of benefits, so for collaboration and validation of these models. So finally, of course, there are many challenges still remaining, but hybrid modeling seems to be quite promising in a sense for thermal dynamics, as they combine the best of the both worlds and also suggest some reusability of the models. But what I would like to maybe stress out in terms of the modeling the thermal dynamics, that what is very important for us now is the generalization of the standards for validation and verification, standard calibration procedures, and guidelines for minimum performance requirements. To sum up, as I mentioned, so as I mentioned, the hybrid model seems promising. There are still challenges, mostly related to the absence of the standardized approaches and issues with the data quality and quantity. So I have some references here if someone is interested to know more, and I'm open for your questions.
Thank you, Lina. Any questions? Again, I have one. Have you tested this hybrid model with different accuracy level of digital twins, like having tried very low accuracy digital twin and how it compared to the high accuracy one?
Well, in this case, the digital twin is more helps for us to validate the models. So in a sense that we have tried to apply these models for different buildings in the same, let's say, area. And we wanted to have similar buildings so we could also compare if let's say, the predicted parameters, they seem reasonable in terms of each other. So it could allow this kind of peer-on-peer comparison. But in terms of the digital twin itself, I think that the benefit here is just to the user to see that if it brings some kind of, I don't know, confidence in the model, and maybe there's something that you can clearly see that it doesn't really make sense. So you can maybe have some kind of prompt that says, okay, the lower upper boundary was hit, or maybe this parameter doesn't make sense, let's rerun the optimization and so forth.
Yeah.
So.
Any other questions? If not, thanks again, Lina. Our next presentation is from Linda van Beers, and it's about lint flow predictions.
Thank you very much. My name is Linda van Beers, and I am a software developer and computational engineer at Arab in the Netherlands. And today I will be presenting Preact, which is a tool for pedestrian-level wind flow prediction through machine learning. Oh, I had a video here, but it doesn't seem to be playing. But what that is showing is basically how wind environment can affect us when we are walking around the city. Like, we've probably all been in the situation where you walk around the corner of a tall building and suddenly you are hit in the face with a gust of wind that you weren't expecting. And this can give problems, and it's often due to those tall buildings that we see more and more in our cities. Oh. And it's not just a problem in the physical sense, but also wind has traditionally been a bit of a problem child in the design process. It can only really be evaluated through very expensive and time-consuming simulations, either in a wind tunnel or through CFD, that take a lot of time to prepare, and then also a lot of time to run for each variation that you want to test. So we can't really do many tests at all. It's also quite a new field, wind engineering. So before we had a lot of cases where actually only when a building was constructed, we noticed, okay, the wind environment here is actually not very good, and you get solutions like this, which are costly because you have to design them after the fact. They're also a bit costly in the aesthetic sense of a building, and they only have a very small effect at a very local scale. Luckily, through CFD and wind tunnel assessments, we are already able to take interventions earlier in the design phase. Usually this is kind of at the stage where we are starting to make a definitive design. We can make a few small changes, but we're not really able to change much about the volumes of the building, which is actually where we can make the most or have the largest effect with the least cost to changing the design. So that is where we want to go, like right there on the top of that curve, large effect, low cost, we want to play with volumes. And of course, this is not only true for wind. There are many KPIs that benefit from being taken into account very early in the design stage. So that is why we have developed this platform, Arab Inform, where we are already able to take many KPIs into account in a generative design process, and also enable the user to kind of play with that, explore the design space themselves, so that the developer can also see what the effects are. However, currently, we're not doing that for wind yet, or actually now we are, but just until very recently we weren't, because this is the kind of project that we would be looking at. This is in the center of Rotterdam, and we generated 10,000 design variants, and we're able to check all of those KPIs that I showed before. And it took us just like about 2 days. But if we would want to take wind into account with the capabilities that we have, which is CFD, pretty much, it would take over 5 years. Well, that, of course, is not the amount of time we can use to make a design. And that's where we came up with a surrogate model, which is trained on synthetically generated urban landscape that we have simulated with CFD, so quite a bit of investment up front.